Hello everyone and welcome to the sixth lesson on the Save My STEM Physics YouTube channel. Oh no, forgive me, the fifth lesson on the Save My STEM Physics channel. Sorry about that. This is the second installment of the quantum and particle physics section of the channel, and today we will be going through spectra, ionization energies, not to be confused with ionization energies in chemistry, and energy levels. So these are a lot of chemistry terms which have different meanings in physics, such as energy levels, which, yes, represent very similar ideas, but there are some differences. And also ionization energies is very different for physics than it is for chemistry. So let's get started with the lesson. Uh, we covered in the last lesson, if you've watched it or if you haven't, I will just go through real quick. Uh, that is a shoddy drawing, but we went through the idea of the electron well, and this isn't an actual thing that you need to know about. It's just a very good concept to have in your head, which helps you understand things. So we imagine these rungs in the well as energy levels that an electron can take up, and electrons naturally reside at the ground state. That should realistically be at the bottom of the well, not just slightly above, but at the ground state at the bottom of the well. Now, as we covered in the photoelectric effects lesson, I would highly recommend going back and watching that video in case there's any information that you're missing for this one. When there is an incident ray, when there's incident radiation on a metal, electrons get excited and move up energy levels. However, if they don't move up enough energy levels with one incident ray, enough to get them out of the electron well, they immediately relax back down to the state that they were in, the ground state. Um, and this is very important for our idea of spectra. So, following excitation, which is when it moves up in energy level, it relaxes. And when this happens, one of two things can happen. There is either UV light released or visible light released. So I will go over very quickly when this occurs. So, ultraviolet light is released. I bring this down here. Ultraviolet light released when it goes from ground state, so GS being ground state. Sorry, give me a second. To any energy level, so we'll just do N for any EL, so the nth energy level. So it could be first, second, third, fourth, depending on how many energy levels the electron can take up. And then it goes back down to the ground state. And this releases ultraviolet light. However, for visible light, oh god, this pen's running out. For visible light, this happens when it goes from the first energy level to N energy level back to, I'll make that more clearly a 1, to the first energy level. And these different spectra of wavelengths of light which can be produced from this and this have names in the specific case of hydrogen atoms. In a hydrogen atom, when this happens, when it releases ultraviolet light of different wavelengths, it's not necessarily one wavelength. There's going to be one wavelength of ultraviolet when it goes from 0 to 1, there's going to be one where it goes from 0 to 2. There's going to be one from where it goes to 0 to 3, and all of them obviously going back down to 0. Same applies for this at the bottom when visible light is released, when it goes from 1 to 2 or 1 to 3 and back. And so therefore, in the first example where there's, we count on our fingers, 0 to 1, 0 to 2, and 0 to 3, there are 3 wavelengths. Now, this isn't an actual real example. This is just an example that I'm bringing up for ease. It might be a real example, I don't know. But yeah, don't take this as something that you actually need to know about the amount. You will be given all the information that you need to figure out the amount in your exam. But it just depends on the amount of variations of things that can happen. So 1 to 2 to 3, there are 3 wavelengths of ultraviolet that can be released. And in the case of hydrogen, when ultraviolet is released, we call it the Lyman series. Lyman. The Lyman series is ultraviolet in hydrogen. For visible light in hydrogen, it is the Balmer series, or Balmer series, as my physics teacher says. So this is visible in hydrogen. Now, as far as I'm aware, I have done other research about this. As far as I'm aware, there are no such names for other elements, so there's no Lyman series equivalent for helium. Not that helium can't release this these spectra of light, just that it isn't named as such, like a Lyman series or Balmer series. And that, I believe, is all we need to go over for spectra, but there are some things that we just need to go over very quickly for energy levels, and this links this to the rest of our quantum physics. HF, which we saw was the energy of the photoelectron in last lesson, so Planck's constant times by the frequency of the incident light, is equal to the change in energy between energy levels. So each energy level, each rung on our electron well, each rank on our electron well, has its own discrete value for energy. So this might be about 2 eV, 2 electron volts. Again, something which you may need a refresher on, which you will find in last lesson, lesson 4, the beginning of quantum physics. This may be 6 electron volts. That may be 9 electron volts. These are all approximate values. The only one that I really remember is to escape you need about 13 electron volts. So I'm basing it roughly off of that. So that means, obviously, you should know that delta is changing. So if I go from the ground state to the first energy level, the change in energy is 2 electron volts. So HF equals 2, because it's 2 minus 0, ground state being 0 electron volts. So you just get HF equals 2 minus 0, HF equals 2, and using that you can actually derive the frequency of the incident ray, because you just do 2 divided by Planck's constant, which I still haven't checked from last lesson. Still not certain what it is. If you'll give me a second to search it up, I will find that out for you. Planck's constant is 6.63 times 10 to the minus 34. So 2 over 6.63 times 10 to the minus 34. Seems like an odd frequency. Yes, that's why it's incorrect. All values for delta E should be done in joules. Something I've forgotten, something I actually did a lesson about. It's about your SI units. So what you want to do is you want to do, if delta E is in electron volts, all you want to do is multiply by 1.6 times 10 to the negative 19. And that should give you a much more appropriate value for the frequency of the incident ray. Um, and that, as far as I'm aware, is all for this lesson. Thank you very much for watching. The next lesson will be wave particle duality and de Broglie wavelength.